you rely upon electronic or electric mechanisms for starting your car. So it says here, a permanent magnet motor uses a permanent magnet, I guess that makes sense, in the rotor and operates on the attraction or repulsion between the rotor permanent magnet and the stator electromagnets. Electromagnets are on the stator in order to simplify the wiring, right? Why not put them on the rotor? Well, because if you put them on the rotor, you're going to need a commutator, right, to power them. If you have your permanent magnets on the shaft, you don't have to power them. But guess what? The permanent magnets can be very heavy. So now you're rotating something which has a substantial amount of inertia. But aside from that, if the permanent magnets aren't balanced right, you could have all kinds of interesting oscillations come in to the motor. It could just vibrate like crazy. But assuming you can get your permanent magnets balanced, the motor's balanced, turns nicely without wobble, then in principle, it's a big win because it's simplifying the wiring, right? Because you don't need a commutator. All of your electromagnets are, I'll say, stationary because they're on the stator. And as a result, all you need to do, or what you need to do, is power those electromagnets in sequence, which is what we did yesterday in lab when we devised the binary numbers that were coming out from our digital ports. And we were basically energizing electromagnets in sequence. So we were using a permanent magnet motor yesterday. We called it a stepper motor, but in fact, the electromagnets were on the stator, the permanent magnets were on the rotor, and we were getting the rotor to turn because of how we energized the electromagnets. So we basically built a permanent magnet motor controller out of the Arduino. And we even used, a substantial current driver in the ULN 2003 Darlington transistor array. So we built a permanent magnet motor driver yesterday and programmed it. How exciting. So here's a so-called unipolar stepper motor. And you can kind of see there's an electromagnet in here you can energize, one over in here you can energize, and then there's another set of wires that you can energize. If the wires that are common are wired together, those are the center wires in the electromagnetics, then you can reduce the number of wires that you need to power this thing. And as you may have noticed, there were only 4 conductors needed in order to do the power of the system. And there were 2 more conductors for power and ground. So ground was your common wire. And then the 4 conductors that were entered in were going to be coil end 1, coil end 2, coil end 3, and coil end 4. And so when you did power and ground, you were automatically wiring to the common wire for the stepper motor. So that's cool. So this shows a unipolar stepper motor. Resistance between the common wire and coil end is always half the resistance between coil end wires. That's important because if you go to the stock room and you find a stepper motor and you don't know how it's wired up, it's not that hard to measure the resistance between one wire and another and figure out what the common is. And you'll find the common wires will have 0 resistance between them. And then you'll be able to figure out which ones are connected to which coils. Of course, you can always use data sheets for the servo motor if you like. I mean, that works too. So, does this show a unipolar stepper motor? The answer is yes. Yes, it does. So that's it's an interesting point. Here comes, a familiar looking Circuit, what's that?
It's the H bridge.
Yeah, that's your H bridge. You close S1 and S2. No, close S1 and S4, and you get the current to flow one way, or you close S3 and S2, and you get the current to flow the other way. What happens if I close switch S1 and S2? The current flows without going through the motor, and that is called a short circuit. That'll give you a problem, blow a breaker, set fire to something or other. So the H bridge can be used to reverse current through a motor. Just close S1 and S2, and the motor will run backwards. Okay. See this? The motor doesn't run backwards. The only thing that runs is you. You run away because what you've done to this circuit is you've created a short circuit. And if this is a 10 horsepower electric motor being driven something that can actually drive a 10 horsepower electric motor, you've basically shorted out something like 230 volts AC at line current, 14 amps, 20 amps, maybe more. This is not good, right? Sparks will fly. So do not do, right? This is why you have to do the electronic switching or find a fail-safe way to switch between S1, S4, or S3, S2. Moreover, when you open a switch, this is kind of a problem with relays, and it creates a little spark, and that's a no good. That's no good for your relay, because that spark, that'll wear down your contacts, and you don't want that. And I don't want to be the guy who shuts switch S1 and S2. I don't want to be that guy, and you don't either, because then you've really messed things up. Your internship with the electrician will be done. So here's an example of the two different states of the motor of the H bridge driving a DC electric motor. So this is a DC motor which can be reversed. Right? Do this wrong and you will have a short circuit. And those are the two states for the H bridge. So is that true or false? After we've had this little discussion about the H bridge, I'm trying to get it so that you guys don't make the mistake of hooking this and that, right? Because that's your short circuit right there. Don't hook this and that. And you go on the opposite corners with your switches. So if you do this wrong, you will have a short circuit, and that is true. So don't do it wrong. This is one of those you got to be careful things. I mean, if you're an electrical engineer and you're wiring this stuff up, or a computer engineer, you kind of got to know the dangers involved in doing things wrong, because you start making short circuits, you will break stuff. And it might be so spectacular as to be epic. I mean, the sparks will fly, put it that way. Now, suppose I want to slow the motor down. How do I do that? How do I slow it down? Well, one thing I could do is I could open up all the switches, but the motor's still turning. It's turning really, really fast. And it's going to continue to turn until it winds down. I got to put the brakes on. How do I put the brakes on? Well, a motor with permanent magnets, either on the rotor or the stator, is also a generator. It's also a generator. In other words, as it's spinning, current will be coming out. So what you want to do is close S2 and S4, and as the current comes out, it creates a back EMF, which causes an electronic brake on the motor. So then it says here, closing S2 and S4, the only way to hit the brakes. Well, it does hit the brakes, but it's not the only way to hit the brakes. How else can I do that? Closing S2 and S4. This motor, pretend it's spinning. I want to slow it down. I know closing S2 and S4 will slow it down. What else could I close? Any ideas? So if I wanted to, I could close S1 and S3 instead. Anything that shorts this motor out is going to slow this motor down, because what it's doing is it's creating an enormous load, a short circuit. And the generator under load gives you a substantial amount of more resistance to being turned than a generator that's not under load. So what you want to do when you start your home generator because of a blackout is make sure it is not connected to the house. Right? There'll be a tiebreaker next to the circuit breaker box, which will change whether you get your utility feed or your generator feed. Do not put the generator under load when you start the motor, right? You start the engine, because a generator under load is harder to turn than a generator that's not under load. So what you do is you start the motor connected to the generator with the generator unloaded. And then once you get up to speed and you've got torque, that'll be a horsepower peak, right? Because we measure the amount of horsepower that we get from a gasoline engine at its peak, and that happens only when the gasoline engine is turning. Gasoline engines do not have good torque at low RPM. Diesel engines have better torque. Electronic motors have excellent torque at 0 RPM. So shut lines S3 and S1, and that'll put a load on the generator part of the motor and cause it to break. That will be your electronic brake, or electric brake if you like. And then close S2 and S4 if and only if S1 and S3 are opened and you want to do another brake. So you can brake using S2 and S4. So it says closing S2 and S4 are the only way to hit the brakes. And the answer is no, it's not the only way. I can also hit S1 and S3, and that'll hit the brakes too. But you got to make sure S2 and S4 are opened, or else you're going to have a short circuit, right? That voltage is going to go right to ground. And that's not good. So there is an L298. That is an electronic H bridge. I do not know how much those things are. L298. Oh, you know what you do? Go to Octopart. Octopart is a database that searches all the parts and gives you the lowest costs. L298. Oh, here's a development board for the L298. That's expensive, 20 bucks. Gee. And it looks like all kinds of interesting devices here. Let's see if we can sort by price. No, that's not right. You know what? You might be better off with eBay or something. L298N on eBay. I'm sure they sell them on eBay. They shouldn't be too expensive. Well, look, it's 92 cents for the whole board with everything like the screw terminals. And man, I don't know. I couldn't source the parts for this for 92 cents. And this comes assembled. That's cool. In fact, the part, look at the part. The part costs $375. That's the same part here as it appears in here, only it's not even coming with a circuit board. And here's a surface mount device version of it for $1. The H bridge. It's cool, right? So what's this about? Semiconductor H bridges have metal tabs for heat sinks. This enables them to handle higher loads. What do you think about that? True or false? Any ideas?
Is it true?
That is true. Get a little thermal compound and a heat sink and tie it together, and you will with your heat sink, and you'll be able to run this at higher power. In fact, it really is all about the amount of heat you can take away from the semiconductor. I have taken 1 ampere 5-volt regulators and run them underwater, and they'll put out almost 2 amperes. But then what happens is you get a thermal gradient from the die inside of the chip to the outside of the package, where the water acts as an infinite heat sink. And so in my case anyway, because I was running it underwater and because it had a violent reaction to the thermal gradient because it had stressed out the package, it exploded like a depth charge, which is really cool. We should do that in the lab. What's this? What's that? I mean, I know what this is. That's a transistor. And I know what that is. That's another transistor. These are bipolar junction transistors, also known as current-controlled current sources. Here's a base. There's the collector. This is the emitter. I think it says that right here. Yeah, see, that's the emitter. But it's in an interesting configuration, isn't it? What do you think that is? So this is a current-controlled current source, and that's a current-controlled current source. What's this whole thing together? Well, that's a pair of transistors. But when you pair transistors in this configuration, it's called a Darlington pair, or in aggregate, a Darlington transistor. So when we were using the ULN 2003 chip for driving our little stepper motors yesterday in lab, we were using an array of 8 Darlington transistors on a chip. So that way you can control much larger current. And it says here, you can control much larger current with Darlington transistors than any individual transistor. And that is correct. That is true. And there he is, Sidney Darlington. He was an AT&T Bell Labs employee. Sidney Darlington, 1953, I think. There it is. Patented the Darlington transistor pair in 1953. And this is patent, whatever. If you want to look up a patent, you guys know how to do that? There's a thing called Google Patents. Put in a number. And this is not the right number, is it? What happened here? Semiconductor signaling device. He's giving me the European patent and not the US patent. Yeah, there it is. 2005. I know what to do. Put this in here. And 2 in there. Put US. There it is, semiconductor signaling translating device. That's what I'm talking about. So because I put the US in front of it, I didn't have to look at the European offerings. And so here we have it. filed 52, and then issued, and there's the Darlington transistor pair. And here's a configuration with 3 transistors. So I guess you could just keep going, right? Why not have 10 transistors and just put them all in parallel like this? And then in principle, you could have, a whole bunch of power. And then you can read the patent if you like. So that's Sydney Darlington. Oh, and here's the link for the patents. Oh, stupid me. So now you can just click on it. Go figure. So let's see. AT&T Bill as employee, titled it's a sole inventor. Is that true? Well, we can look up the patent and see, just in case we're wondering. And here it is. Here's the patent. And here's the guy's name, Sydney Darlington, in Morris County, New Jersey. Now, it says here, assignor to Bell Labs. What does that mean? What's up with being the assignor? What's that? Anybody ever read about patents before? So the assignor is the person who basically owns the patent. So this person was working for hire. They assigned their intellectual property over to their employer, AT&T Bell Labs, and Bell Labs will be the one that cross licenses it to someplace else like GE or something like this. All right, let's close this out. See what else we got here. So there it is, the ULN 2003. This is a really handy chip because what this will do is it'll give us current from our Arduinos, and we can use that current to drive whatever we like. It does not have to be any one particular thing. It doesn't have to be like a counter or, if you have current, you can drive anything. So this is an array of 7 Darlington transistors. It can sync 500 milliamps. So that's cool. And it can give you up to 50 volts of output. And here's the other cool thing. You can take 2 of these things and stack them on top of one another and solder their legs together. And if you do something like that, you basically double the amount of current that it can draw. So here it says it can sync 500 milliamps up to 50 volts. So that's 25 watts of power coming out of that little Darlington transistor array. It doesn't even have a heat sink, so it must get hot. And that's true. Right? Can sync 500 milliamps of current. So here's another one. If you want more than 500 milliamps, stack one on top of the other, both electrically and physically. And that should get you, well, more current. What do you think? How am I doing here, guys? Is it making sense? Is everybody kind of following along?
Yes.
All right. Thank you. So here's another, this is the schematic of what we did yesterday. The ULN 2003 had 4 inputs. Input, I think they called it in 1, in 2, in 3, and in 4. They went to the ULN 2003A, whose output not only went to the motor, but also went to some LEDs, so we could see the LEDs with their blinking. And we had to wire power and ground. And when you look at the common on this unipolar stepper motor, you see that the common is wired to the center coils, and the center coils end up going to the DC motor, the stepper motor supply. Your Arduino doesn't like going up beyond 5 volts. I mean, you can in principle go a little bit higher, but probably shouldn't. But what about this? What about this guy, the driver chip? What can he do? Stepper motor supply. That's not Arduino motor supply, right? That's the stepper motor supply. So he's got his own supply, can run his own current needs, and he has his very own voltage range, whatever that may be. So, it says here, you can't go higher than 50 volts or 5 volts. Is that true? Can your ULN 2003 handle more than 5 volts? And the answer is yes. Yes, it can. It can go up to 50 volts. In fact, if you had any question about that, you could use the Google. Here's a data sheet. And this one's in a nice form factor, right? Because look at that. That's the J mount. Because these things make a little J. And let's see what else we have in here. Probably just write in the term data sheet. Yeah, that looks like the stuff. Only he added a few more diodes in here to protect against reverse biasing in case a magnetic field collapses. And here's the maximum voltage, 50 volts. So that's pretty cool. Oh, I guess he's going to give me all kinds of interesting characteristics I don't care about. So he asked a question. I can't remember what it was. The common can be wired up to 5 volts. Anything higher, you will blow out your Arduino. The answer there is false. You can certainly go up to higher voltages. You go up to 50 volts. Let's see, 18. Oh, I think this is moving. Oh, yeah, cool. So now you can see the alternating magnetic fields of the electromagnets and how they push the rotor around. So that's pretty cool. Also, you can see the sequence, right? This is 1, 1, 0, 0. Here it is 0, 1, 0, 0. You can just write, this is a timing diagram. You can just read the output sequence directly off the timing diagram. Do you need a microcontroller to generate a sequence for a unipolar stepper? Do you really need that? Well, it's a finite state machine, isn't it? Do I need a microcontroller to create a finite state machine? You guys had digital design, right? Did we ever use a microcontroller to create our finite state machines?
We don't need one.
No, you don't need it. You don't need it. In fact, if you look at the whole thing, probably you could do it with a couple of toggle flip-flops or a couple of D flip-flops, and you're done. Now there's a topic called half stepping. But you can see here, there's a specific sequence. There's a finite number of steps. And now the number of steps is increased. Why would you want to have half stepping? What's that about? Why would I want to increase the number of sequences? I'm trying to decrease the number of sequences. What is that about? Why do I do that? This is called a half-step sequence. It says here, you could build this with 4 JK flip-flops and a 555 timer. Probably don't even need that many, but sure, why not? And that would be a finite state machine design problem. For sure, right? It's a finite number of states. So that's true. Build it with 4 JK flip-flops. Build it with something else if you like. Build it with toggle flip-flops. So this says modern RC servo positions are not defined by the PWM duty cycle, i.e. off versus on time, but by the width of the pulse. What do you think of that one? Any ideas? The answer on that one is true. That's true. Let's see. The maximum amount of force the servo can exert is the torque rating of the servo. So a lot of times you see a servo, the little blue servo, and on the side it says 9 grams. What's that about? I don't know if you can find that easily. 9-gram servo. Yeah, there they are. The little blue servos we have kicking around the lab, the ultra cheapo servos. Those are little 9-gram servos. So let's take a look now again. The maximal amount of force the servo can exert is the torque rating of the servo. True or false?
True.
Yeah, that is true. That's why it's printed on the side. You can know just what it is you can and cannot move, knowing that force. So that is true. So here's one. Position pulse must be repeated to instruct the servo to stay in position. Do I have to repeat position pulses in order to get the servo to stay in one place?
No.
Yeah, in fact you do. In fact you do. I wonder if there's a good illustration of this. Position pulse. So here we go. This is cool. You can see the modulation scheme has shortened the pulse, but that has to be repeated regularly and often if you want it to stick. And it could essentially result in something as simple as, outputting a fixed duty cycle waveform like this one. But it has to keep going. That's the way the servos are working. All right, so we're going to stop now. I'm stopping at question 22, I think it was, wasn't it? Let's see. Yeah, question 22 in EE346. Are there any questions? Any questions? No questions? All right. Well, have a good day. Stay safe and stay dry. And thanks a bunch.
Thank you,
Thank you.
Professor.
Thank you, Chris.
Thank you.